Excellent. So welcome back, everyone. Today we're going through section 2B of the course, and we'll start off with sort of a summary of what we went through at the end of last week, and then we'll kick off with where we sort of finished last week. Now, I asked if you guys could join the Slido, and the main reason that I wanted you to do that first and foremost at the beginning of today's lecture is because we're actually going to start today's lecture with a couple of polls that are going to become relevant at the end of the lecture or towards the end of the lecture. So sort of to sort of see how everybody's understanding grows over the course of the lecture. So this is just the introductory slides, nothing changed from last week that you'll all be familiar with. So we're going to look at two hypothetical questions, and I want you guys to answer these just with your gut instinct, okay, rather than trying to actually quickly scribble down any mathematics or anything. The goal of these is to sort of use your gut and see how well your intuition works. So the first question or the first problem is pretty simple. It's given a certain number. Well, how many people do you require to have in the same room before it's more than likely, so before it's more than a 50% chance that at least two people in that room will share a birthday? Okay, so I'm going to start the poll here, and I've given you a bunch of options. Oh, I want to hide the results. There we go. So I've given you a bunch of options. You can see that there are, there's basically units of 10 from 20 to 50, and then 100 people or 150 people. So go ahead and enter the number that you think. How many people do you have to have in a room before there is a greater chance than not that two of them share a birthday, the same birthday? Now we're talking day, month, not day, month, year, incidentally. Yeah. So there's currently 16 people online. So we'll wait until we get sort of order that sort of a number of responses, and then we'll move on to the next one. Okay. All right, so there's sort of 11 there. I'll let people continue to fill that out as we go. But if you are able, then please do fill out these things, because it's good fun for everyone involved. The next poll the next question that we want to try and ask is what I'm calling the game show question. And this one requires a little bit of description. So the situation or the scenario is that you're on a game show, and in that game show you're given a choice of 3 doors. Behind one of those doors there's a car, and the car is the thing that you want to select, you want to win. Behind the other 2 doors there is some, not a prize, which for the sake of this story are goats behind the other 2 doors. Now, the goal of the game is simply to pick the door that has the car, okay? And let's say you, for example, pick door number 1 here. Now, you don't know what's behind any of them yet. And the host of the game show, knowing that you've picked door number 1, then says, okay, I'm going to open for you another one of the other doors, in this case, door number 3, and I'm going to show you that behind door number 3 is a goat. They then give you the opportunity to change your choice. They say, given that I have opened the 3rd door and there was a goat behind it, do you want to change your guess from 1 to 2? Okay. And the question is, or the question that's relevant is it in your interest, or do you gain an advantage by switching or not switching? Okay, so this is the second poll that we're going to do, and this is it now. I'm going to hide the results again. Okay, so please go onto the Slido and choose whether or not it's better to switch doors, better to stick with doors, or it doesn't matter. Now, it's important to note that the host knows what's behind every door, and the host always opens a door that isn't yours and which has a goat. Okay, good. Now, I can't see the results yet either, so I don't know what you're all picking. But this particular problem has become quite famous over the course of the last couple of years, in particular, for a number of reasons. Even though it was first posed in the 80s and 90s. So we'll have a look at the answers and all that sort of stuff coming up soon. But cool. So we've got sort of 14 answers there. That's good. All right. So those are the two questions that we're going to ponder over the course of the lecture. I'm going to leave those two polls open. I think you should be able to still access them both, but maybe not. Maybe you can only do one at a time. If you can't access one of them and you would like to give an answer and you haven't, then just put a message on the Slido and I'll activate the correct poll again. Okay, so right. Well, that's where we're going to leave that for the moment. We'll come back to both of those polls a little bit later. And what we're going to do for now is sort of continue on with the discussion that we were having last week, which is all about probability and the outcomes of different experiments that we do and how we calculate probabilities of different events. So just as a reminder, as a refresher of what we did last week, so that you all remember, we started out by discussing the different sort of names of things and conventions that we use when we talk about statistics and probability. And those were, just as a reminder, the concepts of outcomes, events, and sample spaces were all very important. So again, if we're flipping a fair coin, so you'll remember that our test from last week was flipping a coin. The outcomes of a fair coin toss are either heads or tails. So there are two possible outcomes. And if we flip a coin twice, then there are four possible outcomes, right? Those four outcomes are heads, heads, head, tail, tail, head, or tail, tail. And this selection of all possible outcomes is what's called the sample space. An event, we said, was a collection of outcomes. So for example, an event being you get one of both heads or tails would have both of these results, right? Because it contains both the head tail and the tail head. You don't care about the order. You just want to know if I get one of both. And so the event here contains both of those outcomes. Pretty sort of simple stuff that we went through quite at length last week. One of the other things to remind yourself of before we continue with this week's lecture is about the calculation of probability. So we formulated that the calculation of probability, or the definition of probability, could be formulated in the limit of many trials, where the probability of an outcome A is the number of observations of that outcome divided by the number of trials. So in the limit where n approaches infinity, this essentially becomes the probability of observing A. Okay, and we define that as sort of the limit argument for the definition of probability. And from this argument of, probabilities coming from fractional representations of particular results, we formulated a couple of probability laws, which are pretty important. So the first being that probabilities must always be between 0, which is impossible, and 1, which means guaranteed, and that the sum of all possible outcomes in the sample space has to be 1, because otherwise your sample space is incomplete. One of the things that we finished last week on, which was quite important, was this concept of independence and how independence actually influences our conclusions in statistics and probability. And the main two things that we needed to take away from that, which are going to come up again this week, are that firstly, your understanding. Sorry about that. I appear to have just been kicked out of Zoom, but I'm not sure how long ago that happened. That's a deception, Anna. I'm not actually at the Institute. Virtual background. So let me try that again. Apologies for the technical difficulties, everybody. I'll be with you shortly. So I'm not sure when that cut out. I'm not sure how much of that you missed. That. Okay. Right. So yeah, like I said, I'm not sure how much I missed. So I guess I'll just continue on from independence. But if I missed out more than that, then please let me know.
Yeah, I think it was.
Super. Thanks very much. So basically, one of the really important things that we discussed at the end of last week was about how independence can bias your intuition or can fool you essentially. And so what we were talking about was how basically the summation of many independent events can lead to probabilities that are counterintuitive, and also that you tend to subconsciously reason poorly about independent events because subconsciously we have a drive to try and assign memory to independent events. And the way in which we discussed that was with the gambler's fallacy. So you'll remember the roulette table where we've observed, many occurrences of the same value, red, when you expect them to be evenly distributed between red and black, for example. And so the discussion that we had on independent probability there led to the concept of the gambler's fallacy. We also spoke about probabilities and how we visualize them. And I'm going to refresh a couple of things here because we're going to see them again this week. So the first of which was something that you saw me scribble on my notepad, and I've now embedded actually within the lecture notes because I think it's a useful tool, which is called the EARN model of probability. EARN being it's a fancy word for a jar. And the second being probability tree. So the probability tree being the fishtail thing that we'll see in a second. So the EARN model, so what you can see here is I've just constructed a simple EARN model where we have an urn, which I've shown here is this very stylishly drawn round bottom vase. And inside that urn, there are balls. And these balls are either striped, which these two, or they are white, monochromatic. And the concept of the EARN model is quite simple, is that probability can be imagined as being, you have an opaque urn, so this thing is not transparent, but rather, one moment, yeah. For example, but rather is totally opaque, and so you can't see any of the contents of the urn, and then you are drawing items out of the urn and using those occurrences as a measure of probability, or using them to intuit something about probability. Okay, and so this is something that we'll use quite a bit today. Let me get rid of my very stylish annotation there. So you can see the example, and the example that we discussed last week was to do with the R function sample, which basically invokes something like an EARN model, or you can think of as invoking something like an EARN model to simulate sort of random events. The second thing that we discussed, the second visualization tool that we discussed was the probability tree. And that's essentially a method of visualization that encodes all possible outcomes or sequences of outcomes. So for example, if we go back to our urn here, there's one monochromatic white ball and two striped ones, excuse me. And probability tree of drawing 2 balls from the urn at random looks like this. So you start here on the left, and your first draw can either be a striped ball given by an S or a white ball given by a W. And you can see that the probability of drawing a striped ball is 66% because there are 2 of them. And the probability of drawing a white ball is 33% because there is 1 of them. After you draw the first ball, you look at it, and then you put it back in the urn. You then pull a second one from the urn. And depending on whether your first outcome, your first draw was a striped ball, then you can subsequently draw a white one or another striped one, and they give you these joint probabilities or these outcomes here. So at the top here, we go striped, then white, and we end up with a striped and white combination. Here we go striped, stripe. Here we go white, white, we end up with white, white. And here we go white stripe, and we end up with the white stripes. Not to be confused with the band. And so you can use the probability tree as a way of visualizing or understanding all the different outcomes, but you can see, and as we discussed last week, this can get quite prohibitive. It can get quite complicated very quickly. I mean, you can just imagine if you had a third draw from this, then you would automatically, make this considerably more complicated. Cool. Now, there we go. One of the visualization tools that we didn't discuss last week, but is going to be useful for some of the discussion that we're having this week is what's called the Venn diagram. Now, I'm sure you'll all be familiar with Venn diagrams to at least some degree. And what we have here is just an example of a sample space shown as omega, which is the rectangle. So the rectangle contains all possible outcomes of an experiment. And then I've given 2 possible outcomes or events, which are labeled as A and B. And you can see that there is some overlap between A and B. And so this is a way of encoding how different events correlate with each other or are independent of one another or anything to that effect. And so you can use Venn diagrams quite robustly and quite diversely in order to construct some really interesting sort of things or try and determine some really interesting properties of probability and of statistics. So we can now go back to our urn, for example, where we had 1 white ball and 2 striped ones. So this is our sample space as the rectangle on the outside here. And the 2 outcomes that we have from a single draw from our urn is the ball is either a white one, which occupies 1/3 of the sample space, or it is a striped one, which occupies 2/3 of the sample space. So this is a perfectly valid Venn diagram. Yeah. Cool. The next thing that one of the utilities of the Venn diagram is in our discussion about independence. So remember when we were talking just then about how independent events are very important in statistics. You can visualize independent events in probability and in Venn diagrams. And so the next little poll that we're going to have here is a very, very quick one, which is to say, is the right diagram here or the left diagram here showing that A and B are independent of one another? So go ahead and take your pick. Which of these 2 Venn diagrams, given what we just said about, this is what the Venn diagrams are and this is how our urn looks. Imagine now that we have a circumstance which we discussed last week where you have 2 events, and those 2 events are independent of one another. Now, which do we think is the correct, or which Venn diagram do you think shows independence? Okay, we've got about 11 responses in, so we'll just wait for a couple more. Okay, I'm very, very happy with these responses because this is counterintuitive. So as you can see, that the majority of people have said that the left is the one that they think encodes independence. Now, one of the things that we learned last week about independence, or rather about independent events, is that the outcome of two independent events cannot change the probability of, the outcome of a first independent event can't change the probability of observing the second independent event. Okay. And now if we look at the sample space, for example, here on the right, and we say we have two observations, right? We observe A first. What happens if we observe A? Well, on the left, A and B are completely disjoint from each other in the sample space. And what does that mean? That means that if I observe A, I reduce my sample space down to the box that contains the letter A. But then within that box, there is no B. There can be no B observation. And therefore, once you observe A, you know 100% that B cannot be subsequently observed. And so this actually informs you about the probability of seeing B. So somewhat counterintuitively, I know the right diagram is actually the one that shows independent events. And the reason for that is because the area of the observation of B, given the sample space, is roughly a third, right? Call it roughly a third. If I observe A, I then reduce the sample space down to the box that contains A, and now there is roughly a third chance, or whatever that fraction is, the same fraction as before, that I can see B. Yeah. And so this overlap, when the overlap between these two things is proportional, then you end up with independent events. We're going to talk about this a little bit later. I know that probably is confusing. Or actually, maybe we're going to do it now. Yeah. Oh, we can do it now. Yeah. So, like I said, this is nuanced, right? It's a little bit complicated, so it's worth understanding. So this is what I said. As you observe A, you restrict the sample space down to being just the things contained within that box. And because A and B are independent, you know that the fact that you have observed A can't tell you anything new about B. And therefore, the probability of observing B can't change. Now, what that means in mathematical terms is that the area of intersection between A and B divided by the area of A has to be the same as the area of intersection of B and the total sample space. So this is what happens when you go from one observation to two observations. And what we're essentially saying is that the ratio between that area and that area is the same as the ratio between the box B and the outer box omega. Okay? And that has to be true if A and B are independent. Now, because the probability of the sample space has to be equal to 1, right? We saw that earlier and remember that from last week. What that means is that if A and B are independent, you can then reshuffle this equation and you just get the probability of the intersection of A and B is equal to the probability of A times the probability of B. And this is the formula that you'll remember from last week, that we said that if you have two independent events, the probability of seeing the two of them is simply the multiplication of their standalone probabilities. Okay, I understand that probably is a little bit complicated, so happy to talk about that more if people would like as we go through. One of the things that we spent a lot of time on, well, all of last week was all about independent and independent observations that aren't dependent on whatever has come before, hence the gambler's fallacy and all that sort of stuff. So going back to our urn diagram, going back to our little urn picture, what we have here is a more complicated urn now, where we have 8 balls numbered 1 through 8 in the jar in our urn. And we're now going to simulate a sequence of 2 observations, okay? And our sequence of 2 observations is going to start with our full urn. We're then going to draw a random ball, and it turns out that the ball that we drew is the number 2. We then put the ball back, and we draw the number 8, for our second ball, okay, by random chance. Now, because the observation of the second draw has no has no input, has no information determined by what we drew first. So the fact that we drew the number 2 didn't change how likely it was that we were going to draw the number 8. These things are independent. Okay? These are standard independent observations of 2 different numbers drawing from our urn. Okay? That means that we can really straightforwardly compute the probability of observing a 2 and then an 8, just like we did last week. And what we find is that the straightforward probability of observing a 2 and then an 8 is just the probability of observing a 2 and then the probability of observing an 8. There's 8 balls in the urn, and therefore the probability is 1 in 64. Okay, pretty straightforward. The question is, how does this change if we don't replace the first ball back into the urn? Yeah. So the situation we find ourselves in now is we have the same urn. We draw our first observation, which again is the number 2, but this time we don't put it back in the jar. What is the probability that the next ball that we draw is the 8? Or rather, what is the probability that we see the combination 2, 8? This is what we refer to as conditional probability. And so when you have 2 observations that are dependent on one another, or rather that have an information exchange between one another, then those 2 events are what we call conditional on one another, right? So here we have the example where we have our sample space of outcomes, which is omega. And in that outcome, in that sample space, there are two events. We call them B and we'll call them A. And what we want to know is, what is the probability that we observe B given that we already have observed A? Okay, so this is where one of the things that we discussed last week around the gambler's fallacy sort of comes back. One of the reasons that we found the gambler's fallacy, or one of the things we learnt in the gambler's fallacy, was that there's a very, very small probability of throwing 25 heads in a row with a coin. But that's before you observe any information. The real question you wanted to ask was, what is the chance I throw the 25th head knowing that I've already thrown 24? And that's a conditional probability, right? And that's where the gambler's fallacy gets you, right? And so this is one of the causes of that fallacy, is the lack of understanding or the lack of recognition of how conditional probability differs from independent probability or joint probability. So we can go back to our urn and we can say we're not going to replace the number 2 after our first draw. And we want to know what this does to the next one. And so you can do this really simply with this situation, because with our second draw, we want to know the probability of 8 given that we've already observed 2. And so the way in which we say this in statistics is we want to know the probability of observing 8 conditioned upon our prior observation of 2. Okay, that's the standard sort of statistical speak for what we're talking about here. So again, this is our picture. Excuse me. We draw the number 2. We don't replace the 2 back into the urn, and then we draw the number 8. What's the probability of drawing a 2 and then drawing an 8? Well, it's the probability of drawing a 2 and then the probability of drawing an 8 given that we already drew the 2, which is 1 on 8 for the first draw, but then there's only 7 balls in the urn. So the probability of observing the 8 given that the 2 is already there is 1 in 7. And therefore, the probability of these two things is 1 in 56. Yeah. This is a super trivial example. A much, much more interesting one is to ask the question, well, let's consider the same situation, but let's change our event space. Let's change what we decide a win is here. And so what we're going to say is that we have a game now where I give you the urn and you have to draw 2 balls from it without replacement. And you win if the sum of your 2 balls that you draw is greater than or equal to 10. So firstly, what is the event space? What is the possible, all possible winning draws? And that's what we've got here. This is our event space E, our set of possible events. And you can see that there's obviously you draw the 8 first, and then you can draw a 2, a 3, a 4, a 5, a 6, a 7, or an 8 again, and you win every time. If you draw a 7, you have to draw 3, and then 4, then 5, and then 6, etc., all the way down to if you draw a 2 initially, you have to draw an 8 second in order to win. So these are all the possible winning draws, winning 2 draws. There are 64 ways, there are 64 ways of drawing 2 balls that, come from an urn containing 8 objects, right, with replacement. And that means, because this is, this is with replacement now, right? Because we're allowing you to draw the same number twice. Sorry, I didn't mention that earlier. So there's 64 possible ways of drawing 2 balls from the bag of 8, from the urn of 8 with replacement. And so we have a 7 in 16 chance of winning the game. That's just given, the number of entries here divided by 64, 7 on 16. So that's pretty straightforward. That's just a standard probability, a standard joint probability or standard event space probability of winning, right? The question, or the real interesting thing, is what happens to the probability of winning if we know that we just drew our first ball and it was an 8. Yeah. How does that information modify the probability that we calculate about whether or not we're about to win the game? So if we first observe an 8, then there's 7 possible draws that are going to give us victory. The only thing we can draw and lose is the number 1, right? And so the event space, given we observe an 8 first, is 8 plus 2, 8 plus 3, 8 plus 4, 8 plus 5, 8 plus 6, 8 plus 7, 8 plus 8. Right? So the probability of winning, given that we first drew an 8, goes from being 7 in 16 to 7 in 8. Right? Huge jump. Because obviously, once you draw that first number and you recognize that you've got an 8, the probability of you winning now becomes a lot higher. Okay, so the conditional probability is vastly different to the joint probability before any observations. And this is a fundamental thing that we're going to keep coming back on. What about if you draw the 2 first? How does that change things? Well, if we know that we draw the 2, then obviously there's only one way we can win. We have to draw the 8 next. And therefore, the probability of winning, given you draw a 2, is 1 in 8. And so this is just a very, very simple demonstration of how observing different initial outcomes, or observing a probability of an event given a particular observation can be vastly different to the joint probability of witnessing the event a priori, and equally importantly, that the probability of an event conditioned on some other event is hugely determined by what that initial event is, right? Because if it's a 2, we're basically hosed. We don't win. But if it was an 8, we win almost every time. Okay, so what you're conditioning on is hugely important. Okay, it's something that we'll keep coming back to over the course of this lecture. We can also visualize the conditional probability and basically just read it off almost directly from the probability tree, which is really, really useful for discrete observations or discrete probability problems. And it might not be something that you use day to day in your academic career, but it'll definitely be something that'll help with the understanding as we go through the rest of this lecture. So we can go back to our EARN. This is our probability tree from before. And you'll remember that we said that the probability of drawing the white ball is 33%. The probability of drawing the striped ball is 66%. And so the joint probability of observing a stripe and a white ball together, agnostic of their order, is 0.22 plus 0.22, right? Because you don't care about the order. So this is a win, this is a win, and your summation is 44%. Okay. So if you wanted to know the joint probability of observing a white ball and a striped ball given 2 draws from the EARN, it's 44% a priori. What about if the first ball that we draw is white? What is the probability then of seeing a white and a striped ball given that our first observation was a white ball? So then this falls out because we don't observe the striped ball first. So we go down here, and the probability of observing a white and a striped ball is 22, and is 22% in the full joint space. But the outcomes that are available to us, the sample space conditioned on observing a white ball first, is now just these 2 outcomes, right? Because if we observed the white ball first, you can't have observed the striped ball first. Right? It doesn't work. And therefore, the probability, the conditional probability of observing a white and a striped ball, given that you observed a white ball first, is 0.22 divided by 0.11 plus 0.22, which is, 2/3, 66%, which makes sense because once we condition upon the white ball being observed first, you're back to the gambler's fallacy, right? Now we just want to know what's the probability that I'm going to pull a striped ball out of the bag, because that's my victory. There's only 2 possible outcomes. I either pull a white ball out and I lose, or I pull one of the 2 striped balls out and I win. And so now we just revert to these 2 probabilities here. And so you end up with 66% chance of winning and a 33% chance of losing. When you ask the question, what is the probability of observing a white and a striped, given that I observed white? Hope that all makes sense. Cool. I'm going to try kick this off again. Since the internet died, my notepad died, which is why I've been annotating with my hands on the screen. Okay. Moving on. So let's go back now to the first of our birthday problem. It's the first of our polls. So the first thing that we looked at was the birthday problem. And we had 11 results, and it's a pretty fair spread, really. There's a marginal preference for 30 odd days. And a pretty uniform spread for 50, 100, some for 150, some for 40, and some for 20. So that's really good. That's really interesting to know. So let's figure it out. We know what conditional probability is. We know what joint probability is. We know what independent events are. Let's compute it. Let's actually do the math. So how many people do you have to have in order for two people to have a greater than 50% chance of sharing a birthday? Okay, let's do it. So this is another example of a statistical paradox. A statistical paradox being something that your intuition says shouldn't be true, but it is, and you can demonstrate it with probability, and basically demonstrates why your intuition is not very good with regards to conditional and independent observations. So the way in which we can calculate this is pretty simple. So we can say, let's make the assumption that there are 365 days in the year. The fact that we didn't do 366 basically doesn't change this at all. So don't worry about that if that was worrying you. And the second assumption that we can make is that birthdays are totally random. Now, that's not true. Birthdays tend to cluster around particular dates. 9 months from holidays are usually a pretty good estimate for when you're going to get an overdensity of birthdays, for example. But assuming that birthdays are uniformly random actually is the worst case scenario, right? Because if it turns out that birthdays group together and we assume that they don't, then the probability that we calculate here is going to be an overestimate of the number of people required before you get to that match. Yeah, so that's important to keep in mind. So we're actually overestimating the numbers here. Okay. The probability of finding two people who share a birthday in a room is 1 minus the probability that nobody in the room shares a birthday. And that should be just pretty obvious from our complementary sets, right? There are only two possible outcomes here. Either people share a birthday or they don't. Therefore, the sample space is shared birthday or not shared birthday. They have to sum to 1. The probabilities of these two things have to sum to 1. So this is pretty trivial. Calculating the probability of people not actually sharing a birthday is quite a bit easier than calculating the probability of them sharing birthdays numerically. So we'll show why that is. Excuse me. The probability of people not sharing a birthday is dependent on how many people we've already observed and what their birthdays are, right? So it's a conditional probability. And so the way you can think about this is that the first person just has to have a birthday, right? Because they're the only person in the room, so they can't share a birthday with anyone, so they just have to have a birthday. So the probability of them having a birthday is 1. The second person who enters the room has to, in order for there to be no shared birthdays, has to have a birthday that's different from person 1. The third person has to have a birthday that's different from persons 1 and 2, etc., 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 as shown by my dots. And so what this is in conditionalized probability is the probability of no shared birthday given 0 other birthdays. So that is obviously 1, because you can't share a birthday if you're the only person in the room. Then multiplied by no shared birthday given there's already 1 other birthday observed, no shared birthday given 2 birthdays observed, etc., etc. And when you want to crunch that into an actual number, it turns out to be really simple to understand, because it's just the probability of you having a birthday in the year is 1. The probability that you don't match the next probability, the next person, is 364, over 365. So there are 365 days in the year. Your birthday is day 1. And therefore, this person, second person, can have 364 out of 365 other days and still be totally, and still not share. For the next person, there's 363 available days, 362, et cetera, et cetera, et cetera. Okay, down to n people. So you can just pull this out, and it ends up being 1 over 365 to the power of n times 365, 350, that should say 64, 63, et cetera, et cetera. We can then calculate this really, really simply using just a formula that is basically this, and calculates the cumulative product of these things. So you're essentially doing a cumulative product of there being n equals 1, n equals 2, all the way through to, I've stopped it at n equals 100 here, which, is probably a bit of a giveaway. And I'm going to pull the poll back up now because this is the answer. So when you crunch these numbers, the number of people that are required to be in a room for there to be a greater than 50% chance that 2 of them share a birthday is less than 23. So the correct answer is of order 20. Now remember, this was an overestimate, given the fact that birthdays cluster together. And so we only need 23 people for there to be a greater than 50% chance that 2 of them will share a birthday. Now, as we saw from the poll, this is certainly counterintuitive. This isn't something that people might naturally assume, except for the 18% who said around 20. Great job. But you shouldn't be surprised that this is something that you don't expect, right? Because this is quite counterintuitive. And one of the reasons why this happens, this counterintuitive result is counterintuitive, is because there is a subconscious trend that people have when dealing with conditional probability to accidentally calculate a different condition than the one which we're actually interested in. And this is going to come up a couple of times. But the one in this case, the main reason that people are driven particularly towards large numbers is because they have a conflation or a mix-up in their brain between the question, any 2 people sharing a birthday and someone sharing the same birthday as me. And those in this context might even sound, just when I say them out loud, like they should be the same thing, but they are overwhelmingly not. And the reason that they're overwhelmingly not is because one of them fixes one end of the pairing, which is you, whereas the other allows the pair to happen between any 2 people in the entire cohort. Yeah, so they're different conditional probabilities. And so if you think about this in one way, the given 23 people, the number of possible pairs of birthdays that exist is over 180, right? It's well over half the number of, it's well over 180. It's well over half the number of possible days that exist in the year. And that's what drives the low probability here, the low number of people that are required, because there are just many more ways to pair together arbitrarily 23 individual numbers than you might necessarily think. If you're wondering why my intuition about that drove me to such a large number, it's because the probability that somebody in a room shares the same birthday as you specifically is actually very, very small, right? And if you actually redo this calculation with the probability that you specifically have the same birthday as somebody else in the room, then what you find is that the number of people that are required before somebody shares your birthday is well over 200, more like 250. But the thing to recognize is that by the time you get to a point where 250 people are in the room and there's a 50% chance that one of them shares your birthday, there are very likely, if not 100% likely, basically 100% likely, that there is at least 2 people in the room who aren't you who already share a birthday, right? So it's all about how you conditionalize and what that can do to the result. Cool. There's no questions yet. Excellent. Okay. How do we compute conditional probability? So we showed our little Venn diagram before. This is our sample space with 2 possible events, A and B, and A and B have some intersection. Our conditionalization basically means that what we want to know is the probability of B given that we already observed A. So we want to know this probability in the intersection here. Yeah. If the outcome lies within A, then obviously the probability has to be A is also B, or A is not B. So that's the intersection of, or the summation of the 2 areas here. This area, oh, that's not what I wanted to do. This area here being A given not B, and the inner area here, A given B, right? And so we have, because obviously if you've observed A, those 2 things, you are within the A circle, and so those 2 things have to sum to 1. And so one of the things that we can learn about conditional probability is that we have this relationship here, okay? Assuming that you have observed A, the probability of observing B conditioned on A or not B conditioned on A has to equal 1, okay? And we can then also use the fact that we designed our probabilities to be relative frequencies, or to originate from the distribution of relative frequency. And what we can do is we can then do a little bit of manipulation, a little bit of playing around here, which, you know, I won't go through in detail, but you can have a read through in your own time. But essentially it's just saying that given the conditionality argument that we have here, and the fact that when we look at the Venn diagram, we know that the intersection of A given B is this inner wedge here, and the probability of B conditioned upon A is also that little wedge. There has to be some proportionality between intersection and conditional probability. Yeah, it's just a visual way of thinking about this. So we can say that there is some proportionality between the intersection, sorry, here the intersection and the conditionality, and then we can use the various, you know, rules that we came up with, or things that we've determined over the course of the last 2 weeks to figure out what this constant of proportionality is. And when you go through and you rearrange all these things, what you find is that the constant of proportionality means that the conditional probability of B given A is equal to the intersection of B and A divided by the probability of A. And what that essentially means is that the conditional probability and the intersection are extremely closely related. The only difference between the 2 of them is that the range of values of the intersection is between 0 and 1. When the intersections, when A is B, the probability of intersection of B and A is 1, right? But the conditional probability of B given A has a range from 0, when the probability of B is 0 because A and B are disjoint, 2 being the probability of A. Right? Okay. So we can look at this again in our Venn diagram, right? And we can basically see that we have the, let's look over here again, where we had our independent events, but these things have some overlap, so they're a non-trivial case. And so we have basically the situation where the intersection is telling us about the probability of observing something that resides within this square a priori. Okay, so the intersection is the probability of seeing this thing a priori without having observed anything. The conditional probability is the probability of observing something in that box given that we've observed A, right? And so that's the distinction. It's basically just to do with the range of possible values and whether or not you're talking about something before observing, a probability before observing any information or after observing some information, is the distinction between intersection and conditionality. Okay. Right. So so that's just saying what I just said. On the left, obviously the intersection of these things is 0, and therefore the conditional probability is also 0 because, you know, the conditional probability is proportional to the intersection. So that's the trivial case. One of the other things that you can notice about this formula here, that the probability, or rather from this formula here, is that because the intersection of two things is independent, sorry, rather the intersection doesn't care about the order of observation because it happens a priori. The intersection of B and A is the same as the intersection of A and B, right? And so because the intersection of A and B is the same as the intersection of B and A, you can rewrite the conditional probability of B given A as this is the main definition, the probability of the intersection of B and A divided by the probability of A. The conditional probability of A given B is equal to the intersection of A and B divided by the probability of B. But because these two things are the same, you can rearrange this formula into the probability, or the conditional probability of B given A is equal to the conditional probability of A given B multiplied by the probability of B divided by the probability of A. Okay, and this, I'm missing a couple of brackets there. This is an extremely useful rule or you know, law. And this is what's referred to as Bayes' rule. And it's, as I say here, it's basically going to form the overwhelming majority of the second half of this course. So you keep Bayes in mind. Okay. Let's go back to something that's a little bit more interesting, a little bit more fun, and let's talk about playing poker. So let's start with a really simple version of poker, a really simple version of the game. The game proceeds like this. You have a standard deck of cards, which has 52 cards in it, and you get dealt 5 cards all face down. Okay? And you want to know what's the probability of you drawing a royal flush, which is ace, king, queen, jack, 10, all of the same suit. It's the highest possible hand you can get in poker. So what's the probability of observing a royal flush, given 5 random cards handed to you on a table? Importantly, the ordering doesn't matter, okay? You don't care if you get the 10 first or the king first or the jack first. You just care that you end up with these 5 cards. And using that information, we can calculate the number of possible ways of combining K of ordering k observations of n objects. So in this case, 5 cards from a 52 card deck using what's called combinatorics. And this is just a formulae for combinatorics, which is said, which if you're speaking it, you say, I want to know what is the number of ways I can construct n choose k observations. So you've got a samples, a set of n, a set with cardinality n, discrete elements, and you want to draw k of them. And you want to know how many different ways without ordering you can draw k objects from your set of n objects. And so we're going to now apply this to our royal flush question. And so we have the royal flush happens only if we get ace, king, queen, jack, 10 all in one suit. And there are 4 suits in the deck. So that means that there is only 4 possible ways that you can get the royal flush hand, right? Given that you've been handed 5 cards out of a 52 card deck. There are, however, 52 choose 5 possible ways of getting a set of cards with anything on them, right? And that's 2.6 million-ish different ways. Okay, so given a random 5 cards, there's a 1 in 2.6 million chance that you get a particular set of 5. Okay, so the probability of being dealt a royal flush is just 4 divided by 2.6 million, and it's 1 in 650,000 odd. Okay, so the probability of you getting a royal flush at any by just 5 random cards is 1 in 650,000. Now, that's not super interesting. That's just the standard. That's the standard joint probability of observing 5 particular cards. Okay. It's equally probable. It's worth noting. It's equally probable. You have the same probability of observing any particular sequence of 5 cards. Right. If I had not said I want the best hand, I'd instead said I want the worst hand, which is, say, all off-suited, all random cards, that would give me the same number here. But let's say now that you're being dealt your cards, 1, 2, 3, 4, and the 5th card lands face up. Okay, and you can see what it is. And that 5th card is the 4 of diamonds. What's the probability that you're going to observe a royal flush, given that the 5th card that you were handed is the 4 of diamonds? Well, obviously it's 0, right? Because if you're handed the 4 of diamonds, then you can't possibly observe a royal flush. So the conditional probability of royal flush given you observe the 4 of diamonds is 0. Yeah. However, let's say that it wasn't the 4 of diamonds. Let's say instead it was the ace of spades. What's the probability now that you're going to observe a royal flush? So what is the probability of the royal flush conditioned on the ace of spades? Well, you can define the events as A being the event that the last card that you got was the ace of spades, which we know is true now, and you get the royal flush. And B is the event that the last card you get is the ace of spades, which again we know is true. So the conditional probability of A given B, so the conditional probability that I see both of those events, given that I saw this event happen, is this formula that we came from earlier. The probability of B is easy because the ace of spades is just a normal card in the deck. It's just 1 in 52. So the probability of getting given the ace of spades is 1 in 52. You want to then know what the probability of this intersection is. And the intersection is the number of royal flushes where the last card is the ace of spades. Okay, that's what's the top here. And the joint, so yeah, the joint probability of getting the ace of spades and having the royal flush is this thing on the numerator divided by the total number of ways of constructing a 5-card hand, right? So that's just this 52 times 51 times 50 times 48. because the cards obviously don't get replaced. So the numerator up here is the number of ways that you can end up with a royal flush given the last card is the ace. Okay. And that means that there are 4 possible cards you can receive first, then 3 possible cards you can receive second, 2 possible cards you can receive third, 1 possible card you can receive fourth, right? So this is the probability of observing a royal flush given that the last card is the ace of spades. And the denominator we just said is trivial. It's the 52 times 51 times 52. And so the probability of observing the royal flush, given that the last card that you have is the ace of spades, is 1 on 250,000 instead of 650,000. Okay, so it makes a huge difference, relatively speaking. Still not a great chance of getting it, but still makes a big difference. Okay, this leads us to the next thing, which is known as the Prosecutors Fallacy. This is such a common statistical fallacy that it's got a name, the Prosecutors Fallacy, and it is everywhere. And so it is extremely important that you understand it. Okay, so the logical fallacy known, which is the Prosecutors Fallacy, proceeds like this. A prosecutor in a court has a set of has a piece of evidence. We call that evidence E. And they argue that the defendant has to be guilty because the probability of finding the evidence, given that that person is innocent, is very, very, very small. Okay, and therefore they say, therefore the person has to be guilty. But that probability that we just counted, that conditional probability of the evidence given the observation of innocence being small is completely it's completely unrelated, irrelevant to the question at hand. The question at hand is, what is the probability of innocence given the evidence? And those two things can be wildly different. Okay. Here's an example, right? Or here's the setup. So we want to know, what is the probability of being innocent given a particular observation of evidence? Now, given the formula that we had on the last slide, we know that that's equal to the probability of evidence given being innocent times the probability of being innocent divided by the probability of there being evidence. Okay? And that denominator is the probability of being evidence, the probability of seeing the evidence given you are innocent times the probability of being innocent, plus the probability of seeing the evidence given that you're guilty times the probability that you are guilty. Okay, this just comes from the summation, where we've said that the total probability of evidence has to be the sum of all possible sub portions of our Venn diagram, where there are two options. You are either innocent or you are not innocent. Those are the two things you can conditionalize the evidence. Okay. What this means is that what people do, rather, is that they assume wrongly that there is similarity, even in order of magnitude, between the probability of innocence given the evidence and the probability of evidence given innocence. But you can see from this formulae that assumption, i.e. that these two things are similar, is clearly violated if this value, probability of being innocent, is large, or if the probability of seeing the evidence given that you are guilty is much smaller than the probability of being guilty. Right? But the first one is the more interesting one, right? The first one is the more interesting one, which is the probability of being innocent being large. Now, you're probably thinking to yourself, this is very reminiscent of the DNA thing that we discussed last week, and it's not unrelated. So the DNA thing that we discussed last week was all about independence, and actually this is particularly bad if you have, this is already bad if you have independent events. So if the evidence and the probability of you being innocent is completely independent of one another, then this is already a problem. But you can imagine how this goes up to a whole nother level of being completely wrong if there is any correlation whatsoever between the outcomes of, evidence and being identified incorrectly, for example. Like, so going back to our DNA example, if it turns out that the reason why we have failures or problematic matches in our DNA database is because actually there's some systematic error that means that you're overwhelmingly likely to get, if you find one match, to find 10 matches, then that makes this even more complicated, right? It makes this even more difficult. And it's worth saying, and I won't hammer on this because we don't have a lot of time left, it's worth saying that this isn't hypothetical. This is a real problem that happens in real life. And there's a very, very famous case of people using statistics very badly in criminal law, which was about a woman in the United Kingdom who was incorrectly or wrongly convicted of having murdered 2 of her children because they both died under suspicious circumstances. And somebody and a doctor presented evidence that basically said the probability of seeing 2 people die at random, given that you are innocent, is basically 1 in 200 million or something to that effect. And the jury then took that on board and used that evidence to convict an innocent person and sent them to prison. And it's not the only time that this has happened. This is why it's called the Prosecutors Fallacy, because prosecutors are particularly good at doing this wrong. And so it's a real thing, and it can affect everyone. It can affect your science. It can affect your inference and how you conclude things about what you're doing. It's a very, very important thing to understand, that there is a vast difference between what you are conditionalizing over. You can actually think of this in a really trivial, super trivial way, which is the lottery. Let's say, what is the conditional probability of winning the lottery given that you buy a ticket? It's very, very small. Probability of you winning the lottery given that you bought a ticket is 1 in however many people bought a ticket, arguably, right? Call it 200 million. What is the probability of having bought a ticket given that you won the lottery? Well, it's 1. It's 100%, because you can't win the lottery if you don't have a ticket, right? And so the conditional probability of winning given a ticket is tiny. The conditional probability of a ticket given you won is 100%. 0 and 100%, right? So these are just the conditionalization argument, or what you conditionalize over, is hugely important. All right, so in summary, 2 things that you should always ask yourself when you're doing statistical analyses. Firstly, what am I interested in? Am I interested in the conditionalization of A given B or B given A? Because they're very, very different things. And the second thing is, am I modeling a possibly dependent thing as if it were independent? Because that will give you vastly different probabilities, as we saw in the DNA. Okay, we're now at the Monte Hall problem. So you'll recall the second poll that we did was the game show. I call it the game show. The game show is known as the Monte Hall problem. And let's see what we have for our results. Aha, excellent. The Monte Hall problem is one of the most famous examples of how conditional probability and your brain do not play well together. Okay? The situation that we find ourselves in is we have our 3 doors. We observe one of those doors contains a car and one of them contains a goat. Oh, sorry, 2 of them contain goats. We pick door number 1. The game show host, who knows what is behind all 3 doors, then opens one of the other two that doesn't contain the car. Specifically, one of the other two that doesn't contain a car. He then gives you the option to switch doors. Is it in your interest to switch doors? Now, the majority of you have said, or rather exactly half of you have said it doesn't matter what you do. Some of you said it's better to stick with your door, and others said it was better to switch doors. But the majority have said, or you know, the most common response, the modal response was that it doesn't matter. What we're trying to calculate when we want to know whether or not we should switch is we want to know what is the conditional probability that there is a car behind door number 1, given that we've observed a goat behind door number 3. Okay, so we can again go through this process of doing the conditional probability. The conditional probability here is the probability of the goat being behind door 3, given that the car is behind door 1, times the probability of the car being behind door 1, divided by all of the different ways that we can observe a goat behind door 3. Okay, and all of the different ways that we can observe a goat behind door 3 is if there is a goat behind door 3 and the car is behind door 1, a goat behind door 3 and the car is behind door 2, or a goat behind door 3 and the car is behind door 3. Now, obviously, that term, the goat behind door 3 and the car behind door 3, is impossible because there's only one item behind each door. So that probability is 0, so it disappears. Okay. The probability that there is a goat behind door 3, given that the car is behind door number 1, is a half. And that's because the host always chooses randomly a door which isn't yours and contains a goat. And if the car is behind your door, there was a 50-50 chance that he was going to pick door 3 or door 2. Makes sense. Excuse me. And the last probability is the probability that there is a goat behind door 3, given that the car is in fact behind door 2. Okay? And that has to be 100% because you have selected door 1, the car is behind door 2, and so the host has to select door 3 in order to show you a goat that isn't behind your own door. Okay, so we have these 3 probabilities. We can then substitute these back into our formulae. And when we do that, what we find is that the probability that there is a car behind door 1, given that we've observed a goat behind door 3, is 1/3. Which makes no sense, right? Because what that means, given that the available sample space, given the available event space left is that there is a car behind door 1 and a car behind door 2, that means that the probability that the car is behind door 2, given you observed a goat behind door 3, is 2/3. You are significantly more likely to win the car if you switch doors when given the opportunity, is what this is telling you. And that makes very little sense intuitively. So how can that be? All right. So we can understand this a couple of ways. One of the ways we can understand this is by looking at our probability tree. So in the probability tree, I've taken what is a very complicated probability tree and I've thrown away all branches that don't produce the results that are relevant to us in this particular problem, in this particular example. So that is that we have observed that there is truly a goat behind door 1, or that there is a goat behind door 2. Okay, which is equivalent to saying that there's a car behind door 1 or a car behind door 2. The probability of those 2 things, given a choice, one or the other, because we've observed the goat behind door 3, is 50-50. Okay. But the probability that you were shown a goat behind door 3, given that the goat was behind door 1, is 100%, as I said, because the host has to show you the one with the goat. And so you can then compute the marginal the joint probability of these two things happening, and you find that the car behind door 2 has a probability of 50%. Conversely, if you were to do the same thing, but now the goat is behind door 2, so the car is behind your own door, the host has a 50-50 shot at which door he opens, and therefore the probability, the joint probability that the car is behind door 1 is 25%, right? And then conditionalizing these two things, the probability of the car being behind door 2 is 50 divided by 50 plus 25, which gives you 2/3. That might not have helped, understandably so. One other way that I quite like to think about this is to imagine the exact same problem, except instead of having one door that the host opens, or instead of having 3 doors, right, there are actually 100 doors. You pick one door out of the 100. Let's say this one, number 1 again. That leaves 99 doors that the host can open. And he then, knowing what is behind every door, he then opens 98 of them, and all of them contain goats. So there is now 98 open doors that contain goats, 1 closed that you don't know what's behind, and the one that you picked. Does your intuition tell you that it makes more sense to switch to this door now? Or does it tell you that it doesn't matter still? And I would argue, intuitively, you start to think, actually, if they've gone through and opened 91, 92, 93, all the way through to 98, and then there's 1 door remaining, knowing that he knows where the car is, your intuition lets you to sort of go, I've got a 1 in 100 chance of knowing where the car is and having picked it correctly at the first guess, but he knows. And that was the 1 door that he didn't open, right? And so your intuition starts to think maybe you should switch. And so that's sort of the Monte Hall problem. This is a really great demonstration of why conditional probability is difficult and why your brain doesn't really work very well with it. The last thing that we're going to talk about in today's lecture is about anomaly detection. It's also to do with conditional probability, but it's all about why detecting rare events is difficult. And it's to do with, again, conditional probability. And it's super relevant to all of us, because one of the things that we do in the natural sciences is we try and detect phenomena. And, you know, all of the easy stuff has already been found, right? Largely speaking. So finding rare and exotic events is becoming more and more what natural science is all about, right? And that then begs the question of, is it more difficult to find rare events, or is it easy? And so, excuse me. And so what we're going to talk about to end today's lecture is about anomaly detection, or detecting rare events, anomalies being rare events. Okay, so let's go with the situation where we have a rare phenomena, which is, for example, the detection of an exotic particle in a collider, or an exotic transient that's happening in the universe. And let's discuss how you actually quantify the probability of detecting a rare event. Given that something has happened in reality, truthfully, something has happened, or truthfully, something has not happened. Okay. What is the probability that I observe something truthful that happened, or that I observe something that I attribute as being truthful, but it is not? And so it is false positive. Okay. Or conversely, What happens if I observe something that is truly happened, but I don't measure it, I don't detect it, so I receive a false negative? Okay. Or conversely, you correctly identify that it is negative, or you correctly identify the thing as having happened. So you have two possible failure modes. One is called the false positive failure mode, and one is called the false negative failure mode. They're called type 1 and type 2, depending on where you look in the literature. Just so you know, that's what, if you see people talking about type 1 failures, that's what they refer to. So let's start out easily. Let's consider the probability of detecting a common event. So what I'm saying is, let's assume that we want to try and detect something, an occurrence, an event that is easy and happens often. Okay, so our common event, let's say, is a decay process, right? So the decay of an atom into another atom, via the weak force. Okay, and let's say that decay process happens with a probability of 40% in some observation window, whatever it is. And you have an experiment that detects the emission from this decay with an accuracy of 60%. So better than 50% of the time, but not great. Your detector successfully detects the emission of this particle, of this decay. And 10% of the time, it tells you that it's detected something when really nothing was there. Okay, so its false positive rate is 10%. What's the conditional probability that you witness a true decay, so that something actually happens in the detector, and that the experimental device tells you that you made a positive detection? Because that's the thing where we publish, right? So the true decay rate is 60%, which means that 40% of the time it doesn't happen. Oh, I've got those backwards, actually. Apologies, those are backwards. No, sorry, no, it's not. What am I talking about? The decay process happens in reality with 40%. The probability that your experiment detects the true decay is 60%, right? Therefore, the probability that a true decay happens and it doesn't detect anything is just 40%, 60 minus 100 minus 60. The probability that it tells you it found something when there is no decay is 10%. And the probability that it doesn't tell you that there was a decay when there wasn't anything is 90%. Okay, so this is the situation that we have. This is our detection matrix sort of thing. And we then want to say, let D be the event that a true decay occurs. Okay, and P is the probability, or rather the event that the experiment goes beep and tells you that there's been a successful decay. Okay, what is the probability that there was a true decay given that my experiment beeped at me? And so you can use this formula that we've had before, and we can calculate the probability of there being a positive beep given that there was a decay times the probability of there being a decay divided by the probability of there being a beep. Okay, and that is the denominator here is the probability of there being a beep given a decay times the probability of decay plus the probability that there was a beep given there wasn't a decay times the probability that there wasn't a decay. And you just plug in all the numbers that we have up here, and what you find is that given that I have observed a beep, the probability that I have witnessed a true decay in this experiment is 80%, which is pretty good, given that our detector was only 60% accurate in telling us whether or not there'd been an actual beep, an actual decay, rather. So an experiment that acts upon an common occurrence need not be super accurate, because the occurrence happens a lot. Kind of makes sense intuitively. How does this change when the event that we're interested in becomes rare? And this is where things get interesting. So we take the same experimental setup, except now the probability of observing our decay in nature is very, very small. Let's say 0.1%. Okay. However, our experiment has massively improved. Our experiment now has a 99.9% accuracy of telling you that there was a decay when there actually was one, and a 1% false positive rate. So only a 1% chance of telling you that there was a positive decay when there actually wasn't one. Okay, so we construct this matrix again. So we now know that if there is truly a decay, then we get a positive detection 99.9% of the time. And if there is no decay, we get a false positive 1% of the time. So our experiment is vastly improved. We then take our formulae, we plug all of our numbers back in, but now with our much, much rarer event, the probability of there being a decay is now only 0.1%. But the probability of there being a detection of that decay is much better. We plug in all of these numbers, and the probability of our observing a detection, given we saw a beep the probability of there being a decay, given that we saw a beep of our detector, is now less than 10%. Despite the fact that our equipment has vastly improved, the probability that we have a false positive is over 90%. And that is exclusively because the thing that we're trying to find is rare. Okay? And so this is the pain of anomaly detection. This is the thing that basically demonstrates that the problem that we have with detection of rare events is that whenever you do this conditionalization, unless your experiment is exquisite, so, you know, much, much better, much lower probability of false positive than the probability of an actual emission, you're always going to get more false positives than you get actual signals, right? And this is a huge problem for something like, for example, gravitational waves, right, where the events are rare. And so there's lots and lots of things that go into these sorts of analyses that try and make their statistics robust to these sorts of things. But it's extremely important for us to acknowledge and to understand how this conditionalization influences our inference. Okay, that is the end of today's lecture. That's where we're going to finish for today. Apologies again for the little technical hiccup in the middle there. If anyone has any questions, then obviously I'll keep the Slido up as I have for the rest of the week, and happy to field any questions now. And otherwise, yeah, that's where we'll end it for today. Thanks for coming, and we'll see you all next week.
Bye.
See you.
Bye.